Rinal, would you like me to start sharing the introductory slide now?
Yes, you can do that.
Is that successful, Rinal?
Yes, can you make it full screen?
Yes, I believe I can. Is that also successful? Rinal?
I think it's okay because yes, I don't know. If you
I
make
mean,
full
are
screen,
you
that is
seeing
fine.
are you seeing full screen or
Yes, I can
I
see.
do at least.
Okay, that's good.
though I'm not sure how to well, hold on. Okay, it's good. Yeah. All right, Rinal, let me know when you like me to start.
Yes, it is your choice.
Uh, Balázs, are you ready?
Yes, I am.
All right. Well, it is my great pleasure to introduce today's speaker, Professor Balázs Bárány from the Budapest University of Technology and Economics in Hungary. Professor Bárány is an associate professor in the Department of Stochastics, where he teaches advanced courses, including probability theory and fractal and geometric measure theory, and actively mentors students in research. Professor Báranya's research lies at the forefront of geometric measure theory, fractal geometry, ergodic theory, and dynamical systems. He has made significant contributions to the study of the dimensional and measure theoretic properties of self-affine and self-similar sets and measures, including influential work on the Hausdorff dimension of planar self-affine sets and on the dimension of the graph of the classical Weierstrass function. His work has appeared in leading mathematical journals, and he is a co-author of the book Self-Similar and Self-Affine Sets and Measures, published in the AMS Mathematical Surveys and Monographs series. Professor Báranya's research excellence has been recognized by several prestigious honors, including the Paul Erdős Prize and the Bolyai plaque from the Hungarian Academy of Sciences. The title of the talk today is Exponential Separation of Analytic Self-Conformal Sets on the Real Line. Please join me in welcoming Professor Balázs Bárány.
Thank you very much.
And I will now stop share.
Yes, and it's my slide. Thank you very much for this nice introduction, and thank you very much for giving the opportunity to speak here on this brand new but very quickly developing nice international seminar. And so what I would like to talk about is this exponential separation for analytic self-conformal maps, but also I would like, and which is joint work with István Kolossváry and Sascha Troscheit. Um, and before that, I would like to introduce some basic things from iterated functions, uh, just to be sure what we are talking about. So first, let X D be a complete metric space, just for generality, complete separable metric space. And on this space, let us consider a finite collection of contractions. Right, so let phi be a finite collection of contractions. So this basically means that the images by every function are closer to each other than they were originally for every x, y from x, and lambda I is somewhere between 0 and 1. It's a well-known theorem, basic theorem by Hutchinson, that in that case, there is a unique non-empty compact set which is invariant with respect to this collection, finite collection of contractions. What do I mean by this invariance? Well, this means that this lambda set is the union of its own images by these maps. It's very easy to construct this set actually, because we are contraction, then whatever favorite point we take from x, and because it's a contraction, then you can find a radius sufficiently large enough. And if you take the closed ball around x naught with radius r, then all these guys are mapped. All these guys, all the maps are mapping this closed ball into itself. So then you can just iterate these maps always and always. So you can construct lambda n, which will be the finite union of every possible iteration of this ball. Well, by I, this notation is nothing else than a sequence of symbols formed by this finite collection of indices corresponding to the IFS. And this Fi represents the function which corresponds to this iteration in this sufficient order. Okay, and then this is always a compact set, so lambda is basically the intersection of all these lambdas, because this is a decreasing sequence of compact of closed sets, closed compact sets. So and here comes the name. This is why we call this phi the iterated function system. And IFS for short, because to construct the attractor, we always take the iterates of it. Okay, and this lambda is called the attractor of this IFS phi. So in the same way, very similar way, we can also define a stationary measure on supported on this attractor lambda. Namely, what we can do is that we can take a probability vector pi, and then there will be a unique compactly supported Borel probability measure what was the notation I was using? It is mu, which is stationary in the sense that mu is the weighted average of its push-forward images by the functions. Okay, so what you can imagine is, in this case, that mu is a stationary measure of a very, very easy Markovian process on lambda. And in the following, so let's say that here is my set lambda. I'm here at the point x, and with probability pi, I jump to the point fi of x. Right? So whenever I am, I toss a coin which has exactly as many sides as many functions I have, and it lands on the ith side with probability pi, and then from this point x, I jump to the point fi of x, right? So this is on lambda a very nice Markovian process, and this mu measure is the unique stationary measure on lambda for this Markov process. And this is what we usually, what I call the stationary measure. If you wish, you can construct this measure exactly very similar way like it was constructed here. But for trying to understand, so one of our goals is to understand these objects, some geometric properties of these stationary measures and these attractors of iterated function systems. And for that, it's very helpful to look at their symbolic representation, because there is a very, very nice and very strong let's say, dynamical property in the background for these iterated function systems. So I define sigma as my symbolic space as all infinite words formed by the symbols corresponding to A, who are the symbols from my IFS. And I equip this space with the usual left shift. So this is a very nice and rich dynamics on my left shift. So basically for an infinite word from sigma, so I is just I1, I2, and so on, then the left shift does nothing, then erases the first symbol and moves the second one to the position of the first, moves the third symbol to the position of the second, and so on and so on. So this is a very, very nice and rich dynamics on this symbolic space. And how can we associate points from the attractor? Well, basically what we can do is defining the natural projection from the symbolic space to my attractor. There are several ways to do it. For example, I can say that pi of I should be the limit of the decompositions fi1, fin. So I take the first n symbol of I, take the corresponding compositions of them, acting on some point x naught, and it will converge uniquely to some point. Or I can use also to define this natural projection my invariant closed balls here, because exactly in the same way that pi of I will be the intersection of, let me move it to the other side, of the images of these closed balls if I take the intersection only up to n, be x naught r. Okay, and one very, very nice property of the natural projection that it somehow conjugates and makes a relation between some kind this Markovian process and the left shift operator, namely pi of I will be fi1 of pi sigma I. Okay, so therefore, what we can say is that basically every point in the attractor has a coding, but this coding is not necessarily unique. So a point can have several kind of infinite coding on the attractor. And also this function is smooth in the sense that it's Hölder continuous, because one can equip very easily the shift space by some metric. And with respect to basically any kind of reasonable metric, this pi map would be Hölder continuous. So the main question is for us that to answer the question how large lambda and these mu measures are, Of course, we must make this question reasonable because how large is a big sense. But in the sense we are interested in mostly is the sense of dimension. And I would like to only emphasize one thing, which is the Hausdorff dimension in this talk. But there are many other dimensions in the business, box counting dimension, packing dimension, of Tricot dimension, Asua dimension. So there are several dimension versions. In this talk, we will be interested in the Hausdorff dimension. And many of the dimensions actually for the business we are interested in coincides. So what is the Hausdorff dimension is asking? The Hausdorff dimension is asking that what is the most efficient cover for a set E? So what is the infimum of those S's for which if I take a cover, so for which I saw, so for we, well, what is this S here? This S here is the smallest S for which the S-dimensional Hausdorff measure is 0. And what is the S-dimensional Hausdorff measure? Basically, it asks that what is the infimum of every cover of the set E, every countable cover, for which the diameter of UIs are smaller than delta. And you also take here the superinum in delta. Okay, so these are just basic definitions, just to recall what is this object. And in certain cases, we can answer this question. So in many cases, X it can be just RD, and the metric on that is the usual Euclidean metric. And if we look at the functions to be similarity maps, which means that I have a scaling, some orthogonal action, and a translation, then in this case, it's easy to see that the Hausdorff dimension of X is always bounded above by the minimum of D, because the dimension, of course, cannot exceed the dimension of the state space. Sorry, not X. My attractor is lambda. So the dimension of the attractor is at most D, because the dimension of course, cannot exceed the dimension of the state space, and S naught, where what is this S naught? Where S naught is these contracting ratios to the power S naught equals to 1. So this is what we call the similarity dimension. And it's really easy to see because using the definition of how we, or the construction of the lambda, if we take every n-length word and every possible n-length iterate of fi of this ball and the images, this is always a cover, right? So in the construction is always a cover, and by choosing n, the length of the iterate is sufficiently large, I can make it as small as I want. And basically for such kind of guys, if I sum up every possible iterate, so I'm summing up the diameters to the power S naught, to the power S, it will be nothing else than the diameter of the ball to the power S times the contracting ratios to the power S, the sum of the contracting ratio to the power S to the power N. So if I want to make this guy close to 0, then I choose S in such a way that this sum is strictly smaller than 1, then of course this cover, the summation for this cover will go down to 0 and it will provide us an upper bound for the Hausdorff dimension. And very similar manner, yes. So in the case, so when do we know that it's actually the dimension? Well, there is one simple case which is called the geometric assumption of strong separation property or strong separation condition, or SSC for short. What does this mean? If you take the images of the attractor with itself, with two different kind of functions, then the images are empty. So there is no overlaps between the images by different kind of functions. And in this case, we know that the Hausdorff dimension of lambda should be exactly this S naught, the similarity dimension. So this is what we call similarity dimension. Yes. And also, the other question is that how large our stationary measure is. Of course, for the stationary measure, we need to introduce the Hausdorff dimension and for measures, but the Hausdorff dimension of measures is nothing else than the infimum for the Hausdorff dimension of those sets which are visible with respect to this measure. And basically, from this, what we can, and yes, and there's an equivalent characterization for that, which says that this should be the essential infimum. So the essential infimum with respect to x, the lim-inf of how fast the measure of a ball with radius r centered at x shrinks down to 0. By the way, this is my sign for the logarithm. Okay, so this weird sign means that this logarithm. So what you're interested in, that what is in which exponent of r does the measure of a ball centered at x shrinks down to 0? You are interested in the smallest exponent because there is no need that this exists as a limit. And you are also interested in what is the smallest value. But again, the Hausdorff dimension of mu in this case would be always the minimum of d and the entropy of the measure, of the entropy of the probability measure divided by the entropy of the Lyapunov exponent. And what the Lyapunov exponent is somehow the average shrinking rate of the nth image, right? So if I take the nth iterate of the lambda, I'm asking what is its diameter, then more or less e to the power n times this quantity will be its diameter. And also, again, if we have SSC, so if the strong separation condition holds, then again we have equality that the Hausdorff dimension is nothing else than the entropy over the Lyapunov exponent. So there is a big other family of iterated function systems, self-similar iterated function systems, when we have overlaps. And the question is, how can we handle the overlaps or how not? And there is this seminal result by Mike Hochman, which was generalized also in several ways for other kind of dimensions by Shmerkin, and it's extremely useful, which says the following, that if the exponential separation holds, or ESC for short, then let's first define what's the exponential separation. So we have an IFS on the real line of similarities. So IFS on the real line of similarities, right? So in this case, Fi of x has the form lambda ix plus ti. And we say that the exponential separation holds if you can find infinitely many n's, and there exists also a delta in such a way that delta n, who is the smallest distance, so the minimum between every n-length words, in such a way that the contracting ratios of I and j coincide. You are looking at how close the images of 0 are to each other. And this is greater than delta to the power n. Okay, so what you are asking is that if the contracting ratios of two similarity maps agree, then they are mapping the lambda set, the attractor, or an interval into an interval having the same length. So you are asking how much these intervals are differing, right? So this is, let's say, Fi naught, and this is So this is Fi of 0, 1. Let's say this is Fj of 0, 1. You are asking that if these guys has the same length, then what is the actual distance between these two maps? Which is somehow or measuring how much these intervals are overlapping. And what you are asking that not on every scale, but on infinitely many scales, it doesn't matter how rarely, but there should be exponentially separated with some pre-given delta exponent. Okay, and if we have these, then the Hausdorff dimension of the attractor is the minimum of 1, and the similarity dimension and the Hausdorff dimension of my measure mu is again the minimum of 1 and the entropy over the Lyapunov exponent. Why the minimum of 1? Because if there are overlaps, then of course the dimension can grow up to 1, but not above. Even the similarity dimension has strictly larger value than this. Okay. But there are many kind of generalizations for these exponential separation condition, or I mean, many kinds of variants. I'm using this variant. Many kinds of equivalent variants, actually. But there are very important corollaries of that. For example, if your system is algebraic, so if all the contracting ratios and all the translations parameters are algebraic, then you have either exponential separation or exact overlaps. What does it mean that exact overlap? That there exist finite words, I and j, having the same length, such that the corresponding iterates to I and j coincide. So, but if we forbid this, that for every I and j, these iterates cannot be equal, so there are no exact overlap in the business, then all these maps, all the pair of the maps must be exponentially separated by some exponent, and then we have no dimension drop. By no dimension drop, I mean that the dimension is as large as possible, the minimum of 1, and the similarity dimension also for this stationary measure. And actually, the conjecture says there's a conjecture, the exact overlap conjecture, which says that this is the only way how to produce dimension drop. So if your dimension drops, which means that, let's say, the Hausdorff dimension of lambda is strictly smaller than n and the similarity dimension, then the conjecture says that this is the only way, so there should be some I and j finite words for which the corresponding iterates are equal, but the finite word themselves are different. Okay, so the conjecture says that this is the only way how to produce dimension drop, but actually we don't know whether this is the only way how to do that. But there is one very nice result by Rapaport which points in that direction from the 2020, which is beyond this exponential separation. By beyond, I mean he only assumes that if lambda I, so the contracting ratios, are algebraic and no exact overlaps, so it doesn't matter how you choose I and j finite words, fi not equals to fj, then you have no dimension drop. And it's really beyond the exponential separation condition, because there's an example by Simon Baker from 21, and also with Antti Keinmäki independently we gave also a completely different type of example also in 21. Then there exists IFS of similarities such that it has no exact overlap and no exponential separation condition. By this I mean that, of course, if you have exact overlap, then this distance is zero. So delta n is zero, so it cannot be exponentially separated, right? So if you have exact overlaps, it cannot be exponentially separated. However, what we also claim is that although there are no exact overlaps, so all the functions, all the pairwise functions are different, still this delta n goes down with the super exponential speed to zero, and this speed is up to you. So any kind of super exponential speed is in there. Maybe are there any questions at this moment?
I had a quick question. Are we still operating under the strong separation criteria?
No. These are these conditions of Hochmann is really for the case when you don't have strong separation.
Understood. Okay.
Yes, but exponential separation. So you replace this very nice and easy to check condition, which is the strong separation condition, is geometric, with this more flexible, but in some sense harder to check condition. But typical systems, in your favorite sense of being typical, satisfies the exponential separation.
Yeah, thanks.
Good. Okay, but what I was talking about were really about similarities. So all these were really using that all the maps previously were similarity maps on the real line. There is a version, Hochmann extended this result to RD, and also there are extension on the plane and in R3 for these results for self-affine systems. So when your maps are not similarities, but some affine maps, but they are really somehow relying on the convolution-like structure. It's not true that it's in general there is a convolution, but it has kind of additive structure. It's easy to see that these guys must have. So what I would like to actually talk about after this historic introduction is the very recent result by Arya Rapaport. I think it's so recent that it's only appeared on Archive, but he shows the following and extends this strong separation condition to the world of nonlinear maps. So let phi of fi a be on IFS of analytic maps and let me specify what analytic maps I mean. So such that fi belongs to some set which I denote as omega epsilon of the unit interval 0, 1. And what do I mean by epsilon, S epsilon omega over some interval? Well, what I mean is that this is the maps who are analytic on some 2 epsilon neighborhood of the interval I, for some epsilon, for this epsilon. I also want that these are self-maps for the epsilon neighborhood. So the closed, it's a complex neighborhood. So what do I mean by now? B epsilon is complex neighborhood, okay? We will talk about real maps, real analytic maps on the real line, but we need conditions from them to be satisfied on the complex plane in some tiny neighborhood of this of this interval I. So what I mean is that it's self-mapped not only for this epsilon neighborhood of the I interval, but the I interval is also mapped into itself by all these maps. Sorry. And also, I'm asking that these maps should be contractions over this whole closed epsilon neighborhood of I. Okay, this is not a prime, it's just a... Okay, so these are the maps I'm asking. Arya was asking less, but for the further things I would like to do, we need such kind of analytic maps. And what he claims is the following. If the exponential separation holds, that is, again, you can find a delta such that for infinitely many scales, n, if you look at delta n, and what shall be the delta n now? The minimum of the distances of the maps. But what with respect to which distance? With respect to the supremum distance on the interval I, and we always will assume that this interval is the interval 0, 1. So for every different I, j, n length words, and this distance is greater than delta to the n. So this is a kind of natural generalization of the exponential separation from the self-similar world to this world of analytic maps. And in this case, what he shows is that for every mu stationary measure with probability vector pi, the Hausdorff dimension of mu is a minimum of 1, and the entropy over the Lyapunov exponent. And what is the Lyapunov exponent? I forgot to right? And the Lyapunov exponent is the integral of the logarithm of fi1 prime p sigma I absolute value d nu I, where nu is nothing else than my Bernoulli measure with respect to these probabilities. Okay, so basically the Bernoulli measure means in this case that you choose each coordinates in this infinite world independently and identically with respect to these probability vectors. Okay, and in this case, it's also true that my mu measure is the push forward of this new Bernoulli measure. This is the relation between my stationary measure and the Bernoulli measure. Okay, and in particular, you can also write that the Hausdorff dimension of the attractor is a minimum of 1 and the conformality dimension. But the conformality dimension also needs to be generalized from the linear world to this nonlinear world. And in this case, S naught is the smallest quantity for which, if you sum up for, so so the smallest S, such that if you sum up every map, the contracting ratio of every map to the power S, this series is convergent. So basically, if you think about this, this is again a natural extension of the similarity dimension to this nonlinear world for the non-conformal dimension, because in the self-similar world, this is this guy here. Sorry, this is supposed to be every n-length word. So this guy is nothing else that we used for the covering of my self-similar set, right? This guy here. And if I want this series to be convergent, then setting up this value strictly smaller than 1, how it happened, and also how it happens here. Okay, so basically, if we have exponential separation, we can determine both the dimension of the attractor and the dimension of every stationary measures. So in his paper, Ariel did not provide explicit examples. What he provided, that if you have a nice parametrized family of analytic iterated function systems, which are also parameterized analytically, and you have a one-dimensional parameter family, so your parameter family is one-dimensional, then out of a zero-dimensional set, almost every IFS will satisfy this condition. So in somehow he showed that in a good measure theoretic way, almost every analytic iterated function system satisfies this exponential separation condition. But he did not provide any explicit example. And basically, the world of analytic iterated function systems is horrendously large. Basically, in the self-similar regime can be described by 2 times as many parameters, as many functions I have, but the analytic world is very horrendously much bigger. And the other question is, what we would like to understand, that how typical in this system this exponential separation is. And for that purpose, we introduce something which we call the dual IFS. And for the first side, it will be absolutely no clear what's going on, but I hope that after 15 minutes, it will be. So let's assume that we have such kind of analytic IFS that all these maps are coming from this S epsilon omega family. But we will define maps, Fi maps, who will act on analytic functions in the epsilon neighborhood of the interval I. So I will actually define operators, if you wish, Fi operators who are acting on such kind of analytic maps who are analytic on the epsilon neighborhood on the interval I. Again, don't forget that this is a complex epsilon neighborhood. And how? Well, Fi of h at some point x should be the second derivative of x divided by the first derivative of x plus the first derivative of x times h of Fi. Okay, so at the moment, it's just some kind of random operator derived from my original IFS. But it has some nice properties. For example, this space with the this space with the supremum norm over this epsilon ball is a nice, complete, separable metric space. So I have then a dual attractor. So there exists how did I denote it? I don't know. So there exists a unique compact set which is invariant with respect to these operators and also non-empty. Right? And this is basically a subset of these analytic maps. And also we can define in this way natural projection from the symbolic space to the set of analytic maps by taking, let's say, hi. So I is an infinite sequence of symbols, and hi of x should be, again, the limit as n goes to infinity of Fi of these operators acting on the pregiven order on, let's say, the constant zero function. And basically, in this way, I can also write this guy in some summation form. So Fin second derivative divided by Fin first derivative at the composition of these symbols, but in reversed order. So Fin minus 1 is outside and goes Fin inside times the derivative of this Fin minus 1. Oh, I don't have enough space, so let me make some more space for myself. That's the good part in doing the presentation on a tablet. This cannot be done on the blackboard. Okay, so this is just a formula for these natural projections. But you might say, why is it good? Is it good for the following reason? So what we showed is the theorem: if the dual IFS satisfies the strong separation condition, then the original IFS has exponential separation condition. So basically, we replace somehow some non-geometric condition in the original space with a geometric condition, but in a weird space. But fortunately, it's not so weird as it looks like. Because what does the strong separation condition means in that context? Basically, it says that, okay, here is my interval 0, 1, and I also know that there are some bounds, let's say lower k and upper k, such that every function from my set y must be from here, right? So every function must come from this interval. Every function must be bounded above by k and bounded below by lowercase k. So then I can ask, what is the image of this by some iterates? Let's say this. So this is the fi image of the functions coming from, let me very briefly call it this interval kk. This is all the maps for which we are bounded between capital K and lowercase k, okay? All right? So every function, if I take a function from this, so bounded from above and below by lowercase and uppercase k, then this function doesn't matter how inside, but it must be within this tribe. And what you need to do to check the strong separation is go to very high iterates and try to find this phenomena, that at some moment these tribes are separating each other, right? So if this is the stripe for, let's say, fj of kk, then they are separating from each other in such a way that then no functions can be in both stripes simultaneously. Right? Then if I see this geometric phenomena, then I can be sure that the system, the dual IFS, is strongly separated, and then we guarantee for you that the original system has exponential separation. So this is something which can be geometrically checked. And indeed, using this, we can just build up examples. Like one example is f1 of x, x over 8, f2 of x is x over 8 plus x squared over 32, and f3 of x is x over 8, x squared over 32 plus 29 over 32. Okay, so just by using this geometric argument, it's possible to build up systems for which this dual IFS has strong separation condition. But there is another good property for the strong separation property, namely, it's typical. Typical in the following sense that there exists an open and dense set in the set of IFSs, in the set of IFS formed by maps coming from this S epsilon omega I. And what is the metric there? The supremum metric for each function, for each symbol, and you take the maximum, the sum, whichever you like. But in this sense, there is an open and dense set such that the dual IFS satisfies the strong separation condition, and in particular, it has the IFS has exponential separation condition. So in the sense of topological typicality, the exponential separation condition is extremely typical. Actually, what we could show is that not only the exponential separation condition, but the strong exponential separation condition is the typical, which means that basically the scale, the delta n, who is the minimum. So you can find this universal delta such that if you look at the smallest supraenum norm distance of fi and fj functions whose codings are different, then they are at least delta to the n for every n scale, no matter what. Okay, so even that stronger property is typical in this very strong topological sense. Okay, and I think now my time is slowly over. How much time do I have still?
Yeah, you can take it.
Go ahead, Bernal. Sorry.
Yeah, you can continue then. Yeah.
I can. Okay. So because I think I should explain, because there we got this nice property that there is this geometric property which allows us to check whether an IFS has exponential and actually strong exponential condition or not. And we also can show that it's typical in this topological sense. But why on earth this dual IFS? How did we derive this form? Well, our conjecture and main statement, which we still think we still believe, but we couldn't prove, that this the violation of exponential separation can only happen if basically a reasonable part of your IFS can be conjugated to a linear IFS. So what we believe that actually linear IFSs has this property that they can violate the exponential separation condition without producing exact overlaps. And what we think is that if there is no exponential separation condition, then there exist I and j finite words and also G analytic map such that if you conjugate Fi with G and Fj with these G maps, then are similarities. So this is actually not a statement. I should say it as a conjecture again. So this is what we believed, that this is the only way how to violate the exponential separation in this analytic world. But also, since we have analytic contractions from the dynamical systems world, it is well known how to construct its linearizers. So if F is a nice analytic map with a contraction on the interval 0, 1, then I can make a function hf of x very similarly what we had. So the second derivative over the first derivative of x at the kth self-composition of x times the derivative of kth self-composition of x. Okay, so this is how I define my map. But this map is basically nothing else than taking yeah, okay. And basically for every function, for every g, for which you take the second derivative of g and it's equals to hf times the first derivative of g, what you get is that this f function can be conjugated with a linear map. where P is its unique fixed point. Basically, it's easy to see why, because this guy here is essentially okay. Let me go in another way. So if I define g of x as the limit as n goes to infinity, the nth self-composition of x minus p divided by the derivative of f to the power n. For this function, right, it's easy to see that if I apply g if I apply g for f, then this will be a linear map. Right? G f in this case is nothing else than f prime of p times g of x. But now, roughly speaking, the derivative of g is what? Taking the nth derivative of x, nth self-derivative, which is a big product, right? K goes from 1 to n, f prime, f composition in K. And now I take its second derivative again, and I end up with exactly that summation if I normalize also by the derivative, the nth derivative. Okay, so that was the idea. This is how we constructed these. That was the idea because these linearizers are essentially can be generalized for these multiple functions. Yeah. So that was the main motivation for these functions. Yeah. Okay. Thank you very much.
Thank you, Balázs. So at this time, let me ask the audience, are there questions?
I have a question if about the exponential separation condition, the generalized version by RAL.
Yes, it's here.
Yes. If you specialize this to the self-similar case, it's not equivalent to the original definition of exponential separation. So can you comment on why this is not
yes, so the main
necessary?
difference, so the main difference there is that what do you do? Where is Hochmann's? Sorry, yeah, here. So here you take the minimum only for those guys whose contracting ratios are the same. Meanwhile, here you take every minimum. So usually an equivalent characterization for this guy is that to take the f derivative of I at 0 minus f j derivative of 0 plus taking the logarithm and the difference of the logarithm of the contracting ratios. So this is one thing. But the other thing is that if you, instead of at 0, you take the supraenum norm, then if the contracting ratios are the same, then this will be the distance of the supraenum norm. And if the contracting ratios are not the same, then there will be one point where they are exponentially separated with respect to the supraenum norm. So basically, what you get is, if you look at the distance of the supraenum norm in case of similarities, that this is the fi naught minus fj naught if the contracting ratios are the same. And otherwise, it can be shown very easily that if the contracting ratios are not the same, then they will be anyhow bounded by some universal constant times the minimum of the derivative of the contracting ratios. Right, because if this has length this one and the other one has smaller length, although there will be points where coincide, and there might be points, but there will be other points where they will be very far from each other. So basically that's the relation. This is why in this definition this corresponds to the natural generalization.
Thank you.
Are there additional questions for Balázs? All right, if not, let's thank him for a very nice talk.
I thank you very much.
All right, Renal, I'll pass back to you for if you have any announcements.
Yes. So our next talk will be in January, not anymore. Like I think 2 weeks we have off, so you'll get the announcement in the register in the email. So thank you all again for participation. Bye everybody. All have a good weekend.
Yep, thank you everyone.